A national framework for K-12 science education has been collaboratively developed. It has become the standard for high-quality science instruction in the United States. Despite significant efforts to support science teachers in developing their teaching practices to align with this framework, research shows that the implementation of framework-aligned instruction remains limited. This gap is both practical and epistemological, with existing studies often highlighting what teachers are expected to achieve and where they fall short, but provide little insight into how new teachers reason about the framework. Our study aims to address this gap by exploring how newly hired science teachers in secondary education notice and value science and engineering practices.
The K-12 framework views science and engineering practices as three spheres. The first sphere, investigating, focuses on understanding the real world. The second sphere, developing explanations, focuses on formulating theories. The third sphere, evaluating, focuses on addressing the epistemology of scientific reasoning. Three spheres, with no specific order or hierarchy, transition between each other iteratively, symbolizing the diverse methods and pathways in scientific teaching and learning. The other theoretical framework used in this study is teacher noticing. The study asked teachers two questions during watching classroom videos. What did you notice, and why do you think it is important? The data analysis including three steps: extracting teachers' attending and reasoning of SEPs, mapping the noticing into three spheres, and exploring patterns of the noticing.
Teachers attended to the SEP that was most apparent in the video. When teachers noticed more than one SEP, we referred to it as mixed noticing. Over half of the teachers presented with mixed noticing, incorporating multiple spheres of activity in their noticing. SEP4 emerged as the most frequently involved in mixed noticing. The analysis of the value coding for how teachers interconnected SEP4 and other SEPs resulted in three themes: value for science learning, value for realistic representation of science, and the value for supporting students. For the first theme, a value for science learning, one teacher explained, analyzing data helps students realize new meanings in their learning and supports retention of information. This came from the value in connecting modeling and analyzing data. The main takeaways are, based on our results, SEP4, analyzing and interpreting data, is broadly valued and can serve as a springboard for new teachers to introduce more abstract or challenging practices like modeling. Considering so many of this representative group of new science teachers presented diverse knowledge about SEPs, we call to recognize this knowledge as a communal asset and develop professional learning contexts where teachers can learn from one another and leverage their experiences to support others.
By adopting an asset-based perspective, this study advocates for viewing newly hired science teachers' early perceptions of science and engineering practices as valid and valuable starting points for their professional learning. Building on these early perceptions can help science teacher education programs and professional development programs create learning environments with resources that empower teachers to integrate the interconnected nature of science and engineering practices into their knowledge of instructional practices.